So therefore, we have d of x as 4,000 divided by x plus 3. Good. Good pick. Okay, so let's continue now with the next section, which is 4.2. And in 4.2, we're talking about areas. Okay, so imagine the following function. Let's say a simple function x squared and the interval 0, 2. I'm going to graph this function on this interval. 1, 2. 1, 2, 3, 4. So let me use a different color. Let's say this one. So here's the graph. Very simple function, just between 0 and 2. And let's suppose I would like to determine the area under the graph, under f of x, between 0 and between the x-axis, under the f of x and x-axis. So basically, we're talking about this area. Okay. And I'm going to start by using just n equals 2 subintervals. Okay, I'm going to approximate it with rectangles. Would that be accurate? No. No, it cannot be accurate. But I have 3 possibilities. Using what is called the leftmost point, the midpoint, and the rightmost point. And you can say, what's all this? Okay, so let's start with the leftmost point and 2 subintervals. Okay, I have to determine the width of any subinterval. So width of any subinterval is denoted by delta x, which is 2 minus 0 divided by the number of subintervals. Well, 2 over 2 is 1. So I have 2 subintervals with a width of 1. So if I use the leftmost point for the height is here. So then I don't have really anything for the first one, for the leftmost point. What about the second one? This would be the height. And this would be the area. So I will say the area with the leftmost point 2 is, the base is the same for all of them, 1. The height, f of 0, plus the height here, which is f of 1. Okay, so f of 0 is 0. I don't really need to write the 1 in front, but f of 0 is 0, plus f of 1 is 1. So 1 times 1 is 1. So determining the area with 2 subintervals and the leftmost point, I got 1. Now let's look at the rightmost point. The area with the rightmost point, but I don't want to use the same graph because I will put too many things in there. It will be difficult to see. So I'm graphing it again. So here's the graph. 0, 1, and 2. But this time, I will be using the rightmost point. Okay. So base times height. So this is the first area. Base times height. And this is the area of the second rectangle. So in this case, the area with the right 2 will be base times height. They're all the same. Base is in front. Height, f of 1, plus f of 2. Well, I don't have to write that, but f of 1 I know is 1, and f of 2 I know is 4, so I get 5. Back to the first option with the leftmost point. Is this a overestimated actual area or underestimated actual area?
Underestimated.
Grossly underestimated. Look at how much I'm missing. Thank you. Okay, what about for this particular function? This is not always going to be the same for all functions. For this one, the rightmost point, does it give an overestimation or an underestimation of the actual area?
Overestimated.
Grossly over. All this, what's all that? It's way above. Okay, let's look at the last one with the midpoint. Okay, 0, 1, 2, 0.5, 1.5. So the height, this is the area of the first rectangle. Height, this is the area of the second rectangle. So the area, midpoint, only two subintervals will be base times height plus base times height. I'm not going to even bother with that. It's 1. So f of 0.5 plus f of 1.5. So 0.5 squared is 0.25. 1.25 squared is 2.25. And this is 2.5. As expected, the midpoint is between 1 and 5. Which of these three options you think is the closest to the real area?
Midpoint.
The midpoint. That's the best, the closest. Now, imagine I show the example with n equals 2. Now, here's my question. If I use n equals 4 subintervals, do you think, yes, I have more work to do because now I have to divide the interval by 4. So I will have 1/2 as the width of each subinterval. But do you think I will get better approximations with all three of them? Better approximations with n equals 4?
Yes.
Yes. What about n equals 8? What about 64? What about 128? Well, fitting more and more rectangles in there and determining their area. Will I get closer and closer to the actual exact area?
Yes.
Yes. So what is this process? What am I trying to mimic here? N is 2, and then 4, and then 8, and then 64, and then...
the limit as n approaches infinity.
That's it. So the limit as n approaches infinity. Of what? That's the key. Of the sum of areas of rectangles, right? And that will equal the exact area. Would you agree? This will not be an approximation. This is an approximation. Everything we looked at, all these three examples, are just approximations. But the limit, as n approaches infinity, the number of subintervals gets closer and closer to infinity from the sum of the areas of all rectangles. It will give us the exact area. How do I write this piece is the key next. And then how do I write this piece? That's a different method, a different notation. So let's discuss this first. So you may remember this or not. If we want to write, let's say, A1 plus A2 plus A3 plus dot 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 plus A sub n, I have a sequence of numbers. We don't really like this notation. We like a notation that expresses the sum. So this is the summation notation, also called sigma. It's the Greek letter S, but it's more convenient for what I'm going to write. So this is A sub I. I is from 1 to 2 to 3 to n. I goes from 1 till the last one, n. So at the base of the summation or sigma notation, we write the index 1 to n. And here I have, when I is 1, I have A1, and then the sum says plus, plus. When I is 2, I write A2, and then the sum again says plus. Continue till I is n. So, coming back to this notation. So notice how we determine the sum of areas. Base times height plus base times height plus base times height, depending on how many subintervals I have. Remember how we denote this by? We denote it by delta x. So let me write again, limit as n approaches infinity, from the sum from I equals 1 till the last subinterval of what? Delta x times f of x. Delta x times f of xi. Delta x is fixed, but I, see, I don't have the same. So for the first subinterval, I have 0.5. For the next subinterval, I have 1.5. For the next subinterval, I have 2.5. For the next subinterval, I have 3.5. So that's why this is different for each subinterval. This has a name, Riemann Sum. And it turns out that this is the same with the following notation that we just used. Not entirely and not exactly. So remember, this is on the interval, whatever interval, a comma b. So this is the integral from a to b. We have not seen this before because this is a definite integral. Of course, from f of x dx. And this is the exact area. So remember when we started, I promised to discuss this, to explain what this means. This is what it is. It comes from all these areas. What areas? Delta x f of x. But in the integral, I cannot write delta x, I have to write dx. But they are the same. And f of x is the height for each subinterval, for each rectangle. So that's the f of x. What's this notation? And how do we calculate something like this? Because we know how to calculate something like this, which is an indefinite integral. But we don't know what it means to calculate a definite integral. So that's my next step. So one more time. The area, exact area, is the sum of the areas of all rectangles, base times height plus base times height, etc. All of them. The sum takes care of all of them. And when I put the limit in front, as n approaches infinity, this becomes exact. This is a difficult situation to compute. I'm computing this with my 191 classes, so this is not necessary in this class. But in this class, we need to know how to evaluate this. Okay. So how do we evaluate the definite integral? So here it is. How to evaluate a definite integral. And there is a theorem for that. And the theorem is called fundamental theorem of calculus. It has two parts. In this class, we only look at one. What is that one? that teaches us how to evaluate the definite integral, but it has two parts. Okay, so how do I evaluate that? Now, remember when we were given the function f prime, we determined f of x. If I am given the function f of x and I want to find the antiderivative, we will be using a different notation, the uppercase f. So if I'm given the derivative, I determine f of x. If I'm given a generic f of x, find its antiderivative, I will be using uppercase. And now here it is, the theorem. The integral from a to b. So a to b is the interval we are talking about. In my example, the interval is 0 to 2. Okay, so that's where the AB come from. From f of x dx equals the antiderivative of function f of x evaluated from a to b. How do I do this? I plug in the upper and I subtract when I plug in the lower. So that's what the fundamental theorem of calculus is teaching us. And now